we're ready for hearing last but not least from Martina Rossi, who will tell us about constraining the low mass end of the first stars.
Okay, can you hear me?
Yes.
Yes. So first of all, thank you for giving me the opportunity to present our results. And in this talk, we will talk about how to put observational-driven constraint on the low mass end of the first stars. So, as you know, one of the most fundamental unknown regarding the first stars is their mass distribution. Especially at the moment, we don't know what is the shape of the IMF. We don't know if it could be top-heavy or flat. In addition, we don't know what is the maximum mass for PopIII stars, if it could be greater than 100 solar masses up to 1,000. And finally, what about the minimum mass of PopIII stars? Where PopIII stars with low mass were able to form, we don't know. So, but why low mass end of the first stars is so important? Well, we know that the lifetime of stars is closely linked to their mass. And especially PopIII stars with mass below 0.8, they have a lifetime that is greater than the age of the universe. Therefore, if PopIII stars with this mass were able to form, they could survive as a living relics of PopIII stars. This is why constraining the low mass end of the first stars is so fundamental, because it determines if we will be able to see them or not. So, in our local group, we look for zero metallicity stars among the most ancient and the least chemically enriched system, like the halo and the bulge of the Milky Way, in dwarf galaxies, and especially in ultra-faint dwarf galaxies, Milky Way satellites. In fact, these systems are the least luminous and the least iron abundance ever known. Furthermore, if you look at the color minor diagrams, they show that they had a very short star formation history, and they have a very ancient stellar population. We age greater than 10 gigayears. So are the best system to look for zero metallicity stars. In our work, we focus on PopIII, that is one of the best studied ultra-faint dwarf galaxies, both observationally and theoretically. So we choose as a target. The aim of our work was to constraining the low mass end of the PopIII stars using the non-detection of zero metallicity stars in ultra-faint dwarf galaxies. To do this, we developed a semi-analytical model that describes the evolution of a PopIII-like ultra-faint dwarf galaxies from the epoch of this formation up to zeta zero. The model includes all the most important physical processes, and we calibrate the model using chi-square statistic. In particular, we calibrate the model in order to reproduce the observed properties of PopIII. Here we show the average iron abundance as a function of the total luminosities, and the points represent the data available for ultra-faint dwarf galaxies, Milky Way satellites. As you can see, the color delineates the chi-square confidence level contour, and our fiducial model is represented by the yellow stars. As you can see, in the 99% of confidence level contour, we have PopIII, but also other two ultra-faint dwarf galaxies that are Hercules and Leo 4. This means that our model is able also to reproduce the properties of these ultra-faint dwarf galaxies. So for our fiducial model, we derive the Metallicity Distribution Function, that is the number of surviving stars up now as a function of their iron abundance. In the plot, we show the data in red and in blue our simulation. As we can see, there is a very good agreement between observation and simulation. Of course, since any PopIII stars has been observed so far, we set the minimum mass of PopIII stars equal to 0.9 solar masses to calibrate the model. However, these results are obtained assuming two fully populated mass distribution. So we ask ourselves, is it a good approximation for poorly star-forming ultra-faint dwarf galaxies? The answer is not. In fact, as we can see on the left, we show the evolution of the star formation rate. On the right, we see the comparison between the theoretical IMF in red and the effective IMF resulting from the Monte Carlo procedure in light blue. As you can see, in the first evolutionary phase of the galaxies, the IMF is poorly populated. And even at the peak of the star formation rate, the effective IMF does not converge to the theoretical one, especially for mass greater than 10 solar masses. So we explore what is the impact of the random sampling of the IMF on the expected number of zero metallicity stars in Bootes 1. And what we found is that the fraction of zero metallicity stars increases a lot. So then we explore what is the impact of different IMF, PopIII IMF on the expected number of zero metallicity stars. And in particular, we choose 4 different IMF with three different characteristic mass and the case of the flat IMF. We also vary the maximum and the minimum mass of the PopIII IMF. And the results are shown in this plot, as we can see in this plot, we show the fraction of PopIII stars with respect to the total as a function of the minimum mass for different IMF. And what we can see is that the higher is the characteristic mass of the IMF, the lower is the fraction of zero metallicity stars. In addition, for characteristic mass 0.35, there is a dependence of the on the minimum mass of the PopIII stars, while for all the other IMF, the fraction is independent from the minimum mass. If we consider a higher maximum mass for PopIII stars, as you can see, our results does not change if we assume a maximum mass equal to 1000. So, using a statistical approach, the one of Hartwig, we can derive what is the sample size of the stars that we should observe in order to constrain the minimum mass of the PopIII stars. So here we show the sample size as a function of the minimum mass for 3 different confidence level, and the red shaded area represent the stars that have already observed, we have already observed in Bootes 1. And as we can see, only using 41 stars observed in Bootes, we can already exclude that the PopIII stars have minimum mass below 0.8 solar masses. If you remember, our model is able to reproduce also the properties of Hercules and Leo. And if we consider also these, the total number of stars observed, that the cumulative number, and we derive the same plot for characteristic mass 1, we can conclude that the characteristic mass of PopIII stars should be greater than 1, or the minimum mass greater than 0.8 solar masses at 68% of confidence level. However, it's clear that more observations are needed to put strong constraint on the IMF, on the minimum mass of PopIII stars. So, but what does it mean observe a larger sample size in terms of observation? So, to answer this question, we derive the theoretical CMD for PopIII in order to translate the sample size in terms of magnitude. As we can see, the current limit is set at magnitude equal 19. However, ELT will go deeper in the observation. So we can ask ourselves how deep the observation should be in order to put constraint on the characteristic mass of the IMF. So, as you can see at the moment, we can say something about only characteristic mass around 1 solar masses. However, ELT with ELT and with deeper observation, we will able to get a strong constraint on the characteristic mass of the PopIII stars. So, in conclusion, we can affirm that Ultra-Fain dwarf galaxies are the best system to put constraint on the minimum mass of PopIII stars. And only using 100 of stars, we can start it to see that it is very unlikely that PopIII stars have low mass. And an important thing is that the random sampling of the IMF is required if you want to describe correctly the Ultra-Fain dwarf galaxy systems. So our result. So stay tuned. Our result will be published soon. Thank you. I can hear you.
Sorry, thank you very much for a very interesting talk. Let me ask a couple of questions. So first one is the issue which Tilman also mentioned, surface accretion of metals after the low mass stars form. Could it be that there were low mass PopIII stars, but they no longer appear metal free because they accreted metals?
Yes, but we don't take in consideration this study. We assume that PopIII stars form when the IMS have a metallicity below the critical one. So we don't take in consideration any kind of pollution for PopIII stars.
And then another question that came up by a couple of people is ejection. So low mass stars early on might be ejected from their parent mini halos where they were formed. Could
Yes.
it be that they formed that you assume a closed box system? I assume you sampled the IMF.
Yes, because
could we have lost them due to ejections?
Yes, we described the evolution in isolation for PopIII, and we don't have spatial information about of the galaxy. This is a semi-analytical model, and when there is a sufficient amount of gas, we assume to form stars. So we assume that all low mass PopIII stars remains inside the halo.